AP Calculus students, welcome to 1.3b, Finding Limits Analytically. We already did 1.3a, where we were able to solve limits by using direct substitution. 1.3b today is strategies when direct substitution is not an option. So, whenever you are presented with a limit, all through our course, the very first thing that you're going to do is try direct substitution. Sometimes it works. Certainly it worked for most of the problems in 1.3a. Of course, on the AP exam, that might work once because they want to know, do you know how to do more with the limits they've been giving you? But that's always step number one for the limits. Can you use direct substitution? So today what we're going to look at is you'll see the function that they gave us that they're asking us to find the limit of, we can't use direct substitution. But there is a limit. Okay, we can't make a limit happen when it doesn't, but there is a limit. So what do we do when we can't use direct substitution to solve a limit? What we do is some techniques that we already know, such as factoring, such as dividing, canceling, to write a simpler function that mostly agrees with our first function. We'll talk about that. But we can use direct substitution. So we're going to be using some algebra that you've learned before. A couple things we're going to be learning are a couple strategies we have not learned before, such as on B, rationalizing the numerator. You know how to rationalize the denominator. And we're going to talk about some limits that are proven. We're going to prove them later, not today, so I just need you to believe me. Hopefully you believe me, these are true. And we are going to do some manipulation with some trigonometry. So let's go ahead and read. I am going to read what it says in red, what I already just said to you. That number one, when you are presented with a limit, try direct substitution. Number two, if that doesn't work, can you make a simpler function where you can use direct substitution? So I'm going to go ahead and read in red though. So, number one, what if f of x does have a limit as x approaches c, but the limit as x approaches c of f of x does not equal f of c? In other words, when you try direct substitution by putting the c into the function, you can't solve the limit. So, in other words, you cannot solve the limit by direct substitution. This occurs when functions are discontinuous at x equals c. So what we're going to do is try writing a simpler function. We'll call that g of x, that agrees with your original function at all points, except for f of c. And we'll talk about that. You will understand that better when we actually do some examples in blue. By writing a simpler function g of x, where the limit as x approaches c of f of x does equal the limit as x approaches c of g of x, so they have the same limit, we can use direct substitution to evaluate the limit with our new simpler function by finding g of c. Again, by using direct substitution, where we could not find the limit of the original function using direct substitution. Why is it okay to evaluate the limit as x approaches c of the original function using this simpler function? Because the two limits are equal of the functions, and the limit of our simpler function does equal g of c with direct substitution, meaning then that the limit as x approaches c of f of x does equal the direct substitution for a simpler function. This technique, this is an important point, this technique may reveal a limit that does exist, but it will never force a limit to exist where it does not. Let's try it. So, our first function is we are offered a limit. The limit is x approaches 0 of negative x squared plus 3x divided by x. The first thing you do when you are presented with a limit is try direct substitution. You can see though that when you try to put a 0 into the denominator, it doesn't work. We can't solve this limit. But is there a limit? If there is, can we unveil that limit? So by factoring or dividing, let's see if we can write a simpler function and then use direct substitution to evaluate the limit. So there's a couple ways to go here. Notice that I could write two separate functions with a common denominator. Or notice also in the numerator, there is a greatest common factor of x that I could factor out and then cancel. Let's go with writing two separate fractions and reducing those. So the limit as x approaches 0 of negative x squared over x plus 3x over x is the same expression. And now I'm going to reduce each fraction. The limit as x approaches 0. Notice 1x cancels from the numerator and denominator. I am left with a negative x, and these x's cancel, and I am left with plus 3. So my simpler function is negative x plus 3. Notice now when I try direct substitution, I can solve for the limit, and it is 3. Now what I want to show you on the calculator here is I did on a y1 graph the original function, and on a y2 I graphed our simpler function. So if we take a look here, notice on a y1 and a y2 I put those functions in. Let's take a look at the graph. Okay. Notice as x approaches 0 from the left and the right, the function, there's actually both of them there, does seem to approach a value of 3. Now it looks like there's only one function graphed, but there's actually both of them graphed because they are the same function. But are they really? They are equal at all points except for, take a look at our original function. For x is 0, we tried to put a 0 in for x, and the function is undefined. For our new function, when we try to put a 0 in, we can evaluate it and get a 3. Let's look at the table. And you can see that that is true. Where x is 0, the first function has an error, but the second function has a value of 3. Why is this okay to use a function that is simpler, but not exactly equal to the original? And the key is calculus. Right here, class, when we evaluate a limit, we're only approaching 0. We are not hitting an actual x value of 0. So the fact that they do not have the same y value there doesn't matter. We're only approaching that x value. Let's try the next limit here. Again, notice when I already always check direct substitution. When I try to put a negative 1 into this function, notice I get a 0 in the denominator. Okay, and so I try direct substitution, it doesn't work. Can I write a simpler function? Yes, I can. There's a couple ways to do that. If you notice, the numerator here is the sum of cubes, and you know how to factor the sum of cubes. Another thing you could do is notice that this is actually a division problem, x cubed plus 1 divided by x plus 1. Remember in pre-calc and algebra 2b when I told you you would need polynomial division and you thought I was lying? It's true, you actually need it. Let's do some long division of polynomials. So much fun. Let's write a simpler function. What would I multiply x by to get x cubed? X squared. Let's go ahead and multiply. That would be x cubed plus x squared. And then of course we'll subtract. There we go. We'll bring down our terms that are left. The negative x squared and the 1. What would I multiply x by here to get a negative x squared? That would be a negative x. There we go. We'll multiply negative x squared minus x. And of course, we'll subtract. And your x squareds cancel, and we will write the terms that are left. Oh, look at that. How many times does x plus 1 go into x plus 1? Plus 1. So let's circle that quotient. Let's circle the answer to our division. That is our simpler function. The limit as x approaches -1 of x squared minus x plus 1. This function is exactly equal to the one we started with, except where x is a -1. That's okay. We're only approaching that x, we're not hitting it. Let's try direct substitution. Oh, this works now. A -1 squared is 1, minus a -1 is plus 1, and plus 1, and once again, we have a limit of 3. Class, if you graphed the original function or your simpler function you see here, and you look as x approaches -1, the graph really will look like it is approaching a y value of 3. All right, here's something new. Rationalizing the numerator. You learned in Algebra 2 how to rationalize the denominator. So, whenever you see a rational expression for a limit, and you try direct substitution first, of course. Notice this is frustrating, right? When I try to put a 3 into the denominator, I'm dividing by 0. But is there a limit for this function as x approaches 3? Anytime you see a rational expression with a square root in it, and you feel you need to simplify it, you are going to use rationalizing the numerator, not the denominator. No, I'm serious. Rationalizing the numerator, not the denominator. It's a pattern that you'll need to spot. So, what do? Here's what we do. We look at the numerator. Notice there's 2 terms. The first term is the square root of x plus 1. The second term is 2. There's a minus sign in between. We are going to multiply by the conjugate of the numerator. That would be keeping the terms the same, but putting the opposite sign in between. Of course, we have to multiply the denominator by the same value to keep equivalent fractions. Okay, this looks like a mess. Class, it's not as hard as you think. I really need you to pay attention to this though, because I need you to see my rationale. Okay, I am going to multiply out the numerator. Notice it's not as hard as you think, because when you multiply conjugates, the outers and the inners eliminate. All I need to do is multiply the first and the last. So when I multiply the first terms by foiling, the square root of x plus 1 times itself is x plus 1. I do not need to multiply the outers and the inners. You're welcome to, but they cancel. And I'm just multiplying the last term, which is a -4. Notice I will be able to do a little bit more work here. Now, class, when you look at the denominator, again, now you are tempted to multiply it out because I did that in the numerator. I need you to hear my logic. I am not going to do it, which is nice. I am just going to write the 2 terms that are in the denominator. What is my logic here? My logic here is, look here in the circle, students. This was my problem. This term, x minus 3, was why I could not evaluate this limit, because when I try to substitute in a 3, I get a 0. So I do not want to multiply x minus 3 out here. I do not want to lose it. I want to keep it so I can cancel it. So multiplying out the numerator is easy. Do not multiply out the denominator, because this is the problem and you want it to eliminate. Real next simple step is all I'm doing in the numerator is 1 minus 4. That's all I'm doing. That's x minus 3. Notice what happens then. It's just like magic, students. This is why I love calculus. Notice that the x minus 3 in the numerator and denominator do in fact cancel. And now I can use direct substitution into the denominator to solve the limit. Again, The only reason I can solve the limit is because it actually does exist. I am not forcing a limit to exist where it does not. I have a 1 in the numerator. When I put a 3 into the denominator here, 3 plus 1 is 4. The square root of 4 is 2. 2 plus 2, oh boy, that just works out beautifully. Obviously, we need to do that one more time because doing the rationalizing the numerator is a new thing and it's a heck of a thing. So here we go, students. You are presented with a limit. I check to see if I can use direct substitution. Of course I cannot. I look at the numerator and I'm like, square roots, that's rationalizing the numerator. I know what to do there. All right, let's go ahead and do that. The limit is x approaches 0. All I'm doing right now, class, is writing the same term, the same function here. I'm just giving myself room to multiply by the conjugate. The numerator, the first term is the square root of x plus 5. The last term is the square root of 5. I'm going to put the opposite sign in between. Of course, I have to multiply the denominator by the same. Otherwise, I do not have an equivalent expression. My next job is to multiply out the numerator. Not as hard as you think because I only have to do first and last. Here we go. First terms, I'm going to get an x plus 5. Last terms, a square root of 5 times itself is 5. Again, this looks ugly in the denominator. I'm not multiplying it out. My x is the problem. I need it to go. I need to keep it separate. Take a look in the numerator. Plus 5 minus 5. These x's cancel, and you're left with a 1. You can see the pattern that's happening here. Notice now I actually can evaluate this limit by direct substitution using my simpler function. When my numerator is a 1, and when I put a 0 into the denominator, I get, oh, I forgot a square root right there.
I almost said that, but I didn't want to look foolish.
Oh, you can always, I appreciate that. Yes, I forgot the square root there.
Okay.
Thank you, Bill. You're always welcome to speak up. So when you put a 0 in here, you get a square root of 5 plus a square root of 5, and you get 2 square roots of 5. Now, class, this isn't pretty, but this is what I love about calculus. In Algebra 2, we made you rationalize the denominator all the time. In calculus, we mainly don't do it. That's the correct answer, and you leave it. In class, I'm telling you, on the AP exam, if this was a free response question, you leave it. Do not try to rationalize the denominator. You might make a mistake and then have the wrong answer. You are correct right here, and you need to stop, okay? Now, over here, this is what will throw some students, and I don't blame you because trig can be a little harder, and some of my lovely pre-calc students, last year we didn't get to spend time together on it. So we'll go over this slowly. Here's what I need you to know. First of all, when we have limits, when we're trying direct, oh, I need that 1 in there. When we're trying direct substitution, and there's trig in it. I have 2 limits here in circles. These are proven limits. We have not proven them together. They will later be on a memorization sheet that I have for you, and we will take the time to prove them. We use what's called the squeeze theorem, and we will be doing that together. For now, I need you to believe that the limit as x approaches 0 of sine of x over x is equal to 1. If on your calculator in radian mode, you put this function into your calculator and you looked where x is approaching 0, you would say, oh, that function really does seem to be approaching a y value of 1. Another limit we will prove, but I need you to believe it's true right now, is the limit as x approaches 0 of 1 minus cosine of x over x equals 0. Okay? It does say let's look on the calculator, but we will do that together, and plus this video is getting a little long, so we're gonna keep moving along. Now, here's something I need you to understand also. It doesn't just have to be an x here and here and here and here. This is sine of an angle divided by the same angle. Cosine of an angle divided by the same angle. And the reason why I say that is, class, I could have an x squared here and here, and the limit would still be 1. The sine of x squared over x squared is still 1. The sine of an angle divided by the angle. Same here. I could have 3 theta right here. Sine of 3 theta divided by 3 theta, that limit is still 1. Okay, so it's not just an x, it's the angle divided by the angle. So what we're going to use on number 66 and 68, these are right out of your book. That's where these numbers are coming from. These are right from your book in section 1.3. What if you're asked to evaluate the limit as x approaches 0 of 3 times 1 minus cosine of x over x? So as soon as you see trig, I need you to start thinking here. Now be careful, these limits have to be approaching 0 though. They can't be approaching a different value. The limit as x approaches pi over 2 of this function is not 1. They are both approaching 0. So I'm going to be asking you to look for patterns with trig, just like I'm asking you to look for a pattern rationalizing the numerator. Okay, let's take a look here. The limit as x approaches 0 of this function. Okay, I see trig. I see that x is approaching 0, doing my checking for patterns. Oh, I do know what this limit is. Miss Culver says that it's 0, and it is. What about this 3 out here, though? We learned properties of limits. We know that the limit of a constant times a function is also equal to the constant times the limit, right? It's okay to bring a constant in a function outside of the limit and evaluate the rest of the limit. This expression and this are the same. Okay, I can see above that this limit is 0, and 3 times 0 is 0. So we have solved this limit, and its value is 0. Let's take a look here. The limit as theta approaches 0 of cosine times tangent divided by theta. Okay, I take a look here. I try direct substitution. That doesn't work. I can't put a 0 in here. So I see trig, and so I'm thinking it's one of these limits here. Let me check. Is the angle approaching 0? It sure is. Okay, I think I can use one of these. My problem is I see a cosine, but it doesn't look like this. My problem here is I don't see a sine. This means I need to use some trig identities. You thought you would never use trig identities. You do all the time in calculus. So what do I mean by that? I need this expression to look like one of these. Okay, so here's what I know. The limit as theta approaches 0. I'm going to keep my cosine. If you remember, tangent is sine divided by cosine. Oh, look at that. Trying to write a simpler function. There we go. The cosines cancel. Notice what I have is the limit as theta approaches 0 of sine of theta divided by theta. I made a perfect match right here. This limit is equal to 1. Thank you, students, for hanging out with me and Bill today. And
I never took trig. I'm lost on that. Number 68. Go.
But you did a great job filming, and I so appreciate that. Have an awesome day, and thanks for hanging out with me.